Hello everyone, we are the 7% one and today we are going to introduce to you about route survey. A route survey is a survey used to determine the route, location, and construction of a long-distance transportation or communication line. It supplies data necessary to determine the alignment, grades, and earthworks quantities necessary for the location and construction of engineering projects. Important structures of route survey. Surveys are required for all types of route alignment, planning, design, and construction work. Route surveys range in complexity depending on the size and scope of the project. Small jobs involving a simple road widening or minor improvements may be relatively simple and require a minimum amount of information necessary to prepare plans and specifications. Large complex projects such as brand new multi-lane highway will involve extensive data collection to determine the best location to prepare plans, specifications, and estimates for construction, and to prepare the legal documents and maps required. Here are some structures or transportation routes involved in route survey. First are the highways and roads. These refers to any public or private road or other public way on land. Is used for major roads but also includes other public roads and public tracks. Next are the railways. These are tracks made of steel rails along which trains run. Next are the bridges. These are structures built to span a physical obstacle such as body of water, valley, road, or rail without blocking the way underneath. It is used to provide a passage over the obstacle, which is usually something that is otherwise difficult or impossible to cross. Next are the canals. These are waterway channels for water conveyance or for servicing water transport vehicles. Next is the pipeline transport. It is a long-distance transportation of a liquid or gas through a system of pipes, a pipeline, typically to a market area for consumption. And lastly are the culverts. It is a structure that channels water past an obstacle or to channel a subterranean waterway.
Let us now proceed to the definition of terminologies. These are the basic terminologies and concepts that we must be familiar with as we dig deeper into the topic. First, topographic data. Topographic data is the information about the elevation of the surface of the earth. A frequent task for the surveyor is to stake out the position of a transportation route. This is usually for a new street or highway, but it could also be for a railway, for a long pipeline, or for a transmission line. The shape or geometry of any transportation route is called its alignment. The aim of the alignment selection process is to find a location for the new road that will result in the lowest total construction, land, traffic, and environmental costs. Alignment includes both its horizontal alignment and its vertical alignment. Horizontal alignment. Horizontal alignment of the road comprise of horizontal tangents or straight roadway sections, circular curves, and spiral transitions which depicts the proposed roadway's placement in relation to the terrain and land conditions around it. Next, vertical alignment. Vertical alignment of the road, also called the grade line, consists of gradients or straight lines in a vertical plane and vertical curves typically represented by a profile, which is a graph with elevation as the vertical axis and horizontal distance along the road's center line as the horizontal axis. Next, tangent. A straight line section of a road or railway alignment is called a tangent. Naturally, as the horizontal or the vertical direction of the route changes, the tangent sections of its alignment must be connected by a series of gradual and smooth curves for a safe and comfortable ride. The shape of the curves must be computed by the surveyor so that they can be located on the ground for construction. Next, gradient. Gradient is the rate of rise or fall along the length of the road with respect to the horizontal. While aligning a highway, the gradient is decided for designing the vertical curve. Field surveying activities typically begin with the establishment of horizontal and vertical control points. These are developed to create a framework around which other surveys can be adjusted. These control surveys are used for accurate mapping projects in the transportation road. Horizontal control. Horizontal control surveys coordinate horizontal positional data. These positions can be referenced by parallels or plane coordinate axes. These surveys provide a network of monuments or points on the ground that can be used as a control for any other surveying project, such as a boundary or construction survey. Vertical control. A vertical control survey determines elevation with respect to sea level. These surveys are also used as a benchmark upon which other surveys are based and a high degree of accuracy is required. These surveys are useful for tidal boundary surveys, route surveys, construction surveys, and topographic surveys. Next, easement. Easement defines a situation in which one party utilizes another party's property in exchange for a fee paid to the property owner in exchange for the right of easement. What is the purpose of route survey? First, it determines the best general route between the termini. It eliminates or adds routes or sites which are impractical or unfeasible and to identify the more promising routes or sites. Second, find the optimum combination of alignment, grades, and other details of the selected route. It must blend with each other to produce a system that provides for the easy flow of traffic at the design capacity while meeting the design criteria and safety standards. The highway should also cause a minimal disruption to historic and archaeological sites and to other land use activities. Environmental impact studies are therefore required in most cases before a highway location is finally agreed upon. Third, planning of a right-of-way, the acquisition of fee or easement property and for eventual construction layout work. The center line or right-of-way line is frequently used to determine the position of facilities inside the right-of-way. On the ground, a route survey is used to locate right-of-way lines, a center line, or reference lines in relation to property lines and topographical characteristics. Highways, transmission lines, waterways, ingress and egress easements will be surveyed for suitable position, monumentation, description, and platting, among other things. Lastly, identify the difficulties and restrictions along the road. The purpose of the route survey is to document, turn by turn, the roadways for the load movement and to identify the difficulties and restrictions along the road. The focus is on risk identification and contingency planning for successfully managing risk. Road construction and road delays are included on the road survey. Bridge and overpass clearances, utility lines, and overhead obstacles are also researched and noted. The goal is to ensure that your overdimensional load reaches its endpoint with no damage to the load, road structure, your truck, or other motorists.
We will now proceed to the features of route survey and design. There are three main features that we will discuss for this topic, namely route survey representation, design, and route location. In a route survey, representations of the actual course of the survey and of the plane horizontal features on both sides of it within the limits of direct visibility are plotted on a map board using methods of instrument and exploratory surveying. Instrument surveying includes plane table surveying. Plane table surveying is a fast method of surveying. In this type of surveying, plotting of the plan and field observation can be done simultaneously. In case of plane table surveying, geometrical conditions of site are manuscript in the map sheet using plane table and alidade after that topographic details are arranged on the map. Next is a tachymetric surveying. Tachymetric surveying is a method of determining the horizontal distance, direction, and relative elevation of a point with respect to the instrument station by a single sighting with a tachymeter telescope on a graduated rod. Next is the aerial phototopographic surveying. The aerial phototopographic surveying are done principally as sets of survey jobs to supplement a comprehensive aerial survey. This is done on a larger scale and under different surveying conditions for the purpose of singling out particular objects. Additionally, it is also done for such specific purposes as recording the ice conditions at sea, the boundaries of river flooding, and the centers of forest fires. Another method of obtaining representations of the actual course of the survey is exploratory surveying. Exploratory surveying is an angle-graphic survey of terrain performed with the simplest instruments: a plain table with paper attached to it, a compass, and a sight aiming rule. In an exploratory survey, a map, although not highly precise, is produced directly on the locale. The second feature that we will discuss is its design. The design is determined based on parameters that precedes field of work. Here are the following parameters used for the design. First is the number of lanes. The number of lanes determines the reduction of traffic conflicts, control, and guide people when driving. Next is the right-of-way. The right-of-way refers to the total land area acquired for the construction of the roadway. Next is the maximum grade. The maximum grade affects the operating characteristics of trucks and passenger cars, which determines speed differentials between vehicle types. Next is the minimum radiuses of curves. The minimum radiuses of curves is the shortest allowable design radius for the center line of route tracks under a particular set of conditions. It has an important bearing on construction cost and operating cost, and in combination with super-relevation in the case of routes, and determines the maximum safe speed of a curve. Next is sight distance. The sight distance refers to an adequate sight distance for safe and efficient traffic operation, assuming adequate light, clear atmospheric conditions, and driver's visual accuracy. Next is the fixing alignments. Fixing alignments provides proper guidance to pass the road through the alignment, which is most economical, easy to construct, and free from conflicts. Next is the shoulder width. Shoulder width is a visually distinct area on the edge of the roadway, offering a prioritized space for people to bicycle and walk. Next is the culvert locations. Culvert locations are provided for all natural water courses and drains intercepted by the route. The topography of the land traversed has an influence in the alignment of roads and streets. Topography does affect horizontal alignment, but it is more evident in the effect on vertical alignment. To characterize the variations, engineers generally separate topography into three classifications according to terrain. As the terrain and the gradient increases, the construction cost will increase for a specific design speed. The general classification of terrain are as follows. First is a level terrain. The level terrain is a condition where highway sight distances, as governed by both horizontal and vertical restrictions, are generally long or could be made to be so without construction difficulty or major expense. It is very easy to construct the highway as per the standards. Next is a rolling terrain. The rolling terrain is that condition where the natural slopes consistently rise above and fall below the road or street grade, and where occasional steep slopes offer some restriction to normal horizontal and vertical roadway alignment. Rolling terrain generates steeper grades, causing trucks to reduce speeds below those of passenger cars. Next are mountainous terrain. Mountainous terrain is that condition where longitudinal and transverse changes in the elevation of the ground with respect to the road or street are abrupt, and where benching and side hill excavation are frequently required to obtain horizontal and vertical alignment. Mountainous terrain aggravates the situation, resulting in some trucks operating at crawl speeds. The third and last feature that we will discuss is route location. The development of the interstate highway system and more general acceptance of the limited access principle for major highways have resulted in more and more highway projects being to serve local traffic. Surveys for highway projects where new location is being considered start with a general study of the entire area between terminals, proceed to more specific studies of possible alternative routes, and finally conclude with a detailed survey of the selected route and staking of the final center line on the ground. These procedures are generally carried in three stages. First stage is the reconnaissance. Reconnaissance includes a general study of the entire area, the development of one or more alternative routes or corridors, and the study of each of these corridors in sufficient detail to enable the proper officials to decide which will provide the optimum location. The second stage is location, and the third stage is preliminary.
Location survey is basically a survey that roughly estimates an area. The idea is to figure out whether the property lines, buildings, and any other improvements such as driveways, sidewalk, and retaining walls are on the land and how they connect to one another. All of this information is depicted on a drawing known as location drawing or a house location drawing in some cases. Location surveys or drawings do not accurately identify property boundaries, so it should not be used to establish or locate fences, garages, buildings, or any other existing or prospective improvement. What is the purpose of an approximate location survey? So during refinancing or purchase of a home, a lender or a title insurance company or any other agent will use the location survey as the primary survey instrument. So it offers them a rough estimate or an understanding of where things start and where things usually end. So this is sufficient for them to approve your loan. This is good news because location surveys are far less expensive than boundary surveys.
Factors to consider in design of highway. Highway geometric design refers to the study and calculations done by engineers when it comes to roadways. This is done to guarantee that the highway is designed to meet the topography of a specific location while also ensuring service, performance, and safety. There are various factors that must be taken into account when designing a roadway, including design traffic volume. It is the average density of traffic that can be possible on a road, and it also helps design roads. Level of service. It is the qualitative measures of the possible conditions during traffic, or rather known as the freedom of maneuver. Super elevation. The technique or the process of making the outer edge of the pavement raised on curved roads. Road alignment. It is the positioning of the center or the center line of a road. Grades of a road. It is the measurement of the slope of a road. Lane width. It is the measurement of the lane from left to right. Cross section. It is the section of the road where all the elements and parts are found. Slight distance. It is the sight of what's ahead of the road and calculating the distance if there are any other vehicles or obstacles to avoid accidents. Number of lanes. Highway roads usually have at least 2 lanes. The number of lanes are designed for any vehicle to pass and be guided towards the designated direction and to control traffic. Design speed. The highest speed that a vehicle can travel safely on different conditions of the road and during traffic. Vertical and horizontal clearance are the clearance of the height and width to which only certain vehicles are allowed on the highway.
Preliminary surveys to collect adequate data to prepare a plan or map of the area to be used for planning and design. The preliminary survey is a detailed study of a route tentatively selected on the basis of reconnaissance survey information and recommendations. Preliminary survey includes gathering geospatial data about the proposed route and the project requirements for data outputs. This includes the establishment on the ground of the proposed route and location of terrain and physical features, both man-made and environmental. The preliminary survey serves as the basis upon which the majority of the project is built. Accuracy is important. Minor measuring errors propagated over a long distance may result in regulatory and trespass difficulties. It is more than simply a survey. It is knowing the suitable horizontal and vertical datum, standard data libraries, and laying the groundwork for future project work.
Sight distance available from a point is the actual distance along the road surface over which the driver from a specified height above the carriageway has visibility or stationary or moving objects. The most important consideration in all these is at all the times the driver traveling at the design speed of the highway must have sufficient carriageway distance within his line of vision to allow him to stop his vehicle before colliding with a slowly moving or stationary object appearing suddenly in his own traffic lane. The computation of the sight distance depends on the reaction time of the driver, speed of the vehicle, efficiency of brakes, frictional resistance between the tire and the road, and the gradient of the road. Reaction time of the driver is the time taken from the instant the object is visible to the driver to the other instant when the brakes are applied. The total reaction time may be split up into 4 components. In practice, all these times are usually combined into total perception reaction time suitable for design purposes, as well as for easy measurement. Many of the studies shows that drivers require about 1.5 to 2 seconds under normal conditions. However, taking into consideration the variability of driver characteristics, a higher value is normally used in design. The speed of the vehicle very much affects the sight distance. The higher the speed, more time will be required to stop the vehicle. Hence, it is evident that as the speed increases, sight distance also increases. The efficiency of brakes depends upon the age of the vehicle characteristics, and etc. If the brake efficiency is 100%, the vehicle will stop the moment the brakes are applied. But practically, it is not possible to achieve 100% brake efficiency. Therefore, the sight distance required will be more when the efficiency of brakes are less. Also, say for geometric design, we assume that the vehicles have only 50% brake efficiency. The frictional resistance between the tire and the road plays an important role to bring the vehicle to a stop. When the frictional resistance is more, the vehicle stops immediately. Thus, sight required will be less. No separate provision for brake efficiency is provided while computing the sight distance. This is taken into account along with the factor of longitudinal friction. And lastly, the gradient of the road also affects the sight distance. When climbing up a gradient, the vehicle can stop immediately. Therefore, sight distance is required less. While descending a gradient, gravity also comes into action and more time will be required to stop the vehicle. Sight distance required will be more in this case. Stopping sight distance is the minimum sight distance available at the highway at any spot having sufficient length to enable the driver to stop a vehicle traveling at design speed safely without collision with any other obstruction. Safe stopping distance is a term used in traffic engineering to describe one of the most important measures. It is the distance traveled by a vehicle from the time a situation is first noticed until the deceleration is complete. If drivers must react quickly to a situation, they must allow enough time. As a result, a sight distance is at least equal to the safe stopping distance, and it should be provided in a highway design. The sum of the lag distance and the braking distance is the stopping sight distance. The lag distance, Vt, is the distance traveled by the vehicle during the reaction time t, where v is the velocity in meters per second square. The distance traveled by the vehicle while braking is known as braking distance. This is calculated for a level road by equating the work done in stopping the vehicle with the vehicle's kinetic energy. If F is the maximum frictional force developed and I is the braking distance, then the work done against the friction to stop the vehicle is Fi is equal to Fwi, where W is the vehicle's total weight. At the design speed, the kinetic energy is 1/2 mv squared is equal to 1/2 weight v squared over g, which can be derived more to Fwl is equal to wv squared over 2g, and then to L is equal to v squared over 2gf. Therefore, the stopping sight distance is equal to lag distance and braking distance, and given by SSD is equal to Vt plus v squared over 2gf. When there is an ascending gradient of say n%, the component of gravity adds to the braking action and hence braking distance is decreased. The component of gravity acting parallel to the surface, which adds to the braking force, is equal to W sine A, is equivalent to W tan A, which is equal to Wn over 100, equating kinetic energy and work done. As you can see in this picture in the right side, this is the formula. Similarly, the braking distance can be derived for the descending gradient, which is in the lower right.